this. Do we agree?
Yeah.
Now please tell me, if that's a basic example of an even function, which it is, what type of symmetry would you say this graph has? And when I say symmetry, I mean like reflections.
Y-axis.
Yeah, it's reflected through the y-axis. And all even functions will be reflected through the y-axis. And you say, Professor, where are you going with this? Because eventually what we have to do is to identify the trig functions. Is sine an even function? Is cosine an odd function? That makes a big difference here shortly. Next, Jacob, what was the next definition?
A function is odd if for every number x in its domain, the number negative x is also in the domain, and f of negative x equals negative f of x.
Beautiful. That's the critical part right there. Okay? Now, can you imagine that you're at a major university and all these little handouts are ringing in, you have to do yourself. They're not going to do it for you. They'll tell you what the textbook is, and you're on your own. And they'll start talking about even and odd functions. Wait, I don't know what an even function is. No, they're saying what's in your textbook. Find it. Okay, can anyone tell me, right, quickly, a nice example of a function that you think, when you replace x with a negative x, it comes out to be the opposite of the original function?
X cubed.
X cubed. It's an example of an odd function and would meet that definition. By the way, now to make sure it does meet that definition, here goes, guys. If I try this right here, if I try f of a negative x, in other words, replace that x with a negative x, I get this. Simplify it to get this. And this right here says, just like the definition says, this is the opposite of the original function. Easily shown. Now, I know and you know what the graph looks like for x cubed. Gotta go through it quickly. Now, can anyone tell me if that's x cubed, which it is, what type of symmetry would you say this graph has?
It's rotated 180 degrees.
Beautiful, I like that. Something else. I understand what you said.
Oh, is it?
Okay, I'll give you choices. It's either
Negative
symmetric
x.
about the y-axis, like the first one. It's symmetric about the x-axis, or reflection through the x-axis. Or sometimes it's reflected through the origin.
The origin. The origin.
Okay, so here this is going to be reflected through, or symmetry with respect to the origin.
Could you also say that it's reflected about the line negative, y equals negative?
I got you. That's exactly what I thought you were thinking of. You could. I heard exactly what you said. Okay, guys, that's an example. So now I have an easy example for an even function, an easy example for an odd function. And I see the symmetry, if it's even or odd. Now, it's coming down to it now with these definitions. Over in part 2, Jacob, am I now to the point where I have to identify the trig functions?
Yes.
Okay, hang on now.
You have it written out. Would you like me to just tell you the trig functions?
So you know what? And I would first derive and show you why. Tell me the first one, and then we'll look at a reason why.
Sine
Okay.
negative theta equals negative sine theta.
Now, guys, if I accept that, which of these two definitions, even or odd, does this one look like? Odd. Odd. So sine is an odd function. Now, I did not show Jacob on that handout. I'm sure I didn't show why. Why is sine an odd function? It looks like that definition over there, Professor, but why? Watch what's going to happen here. Just a quick visual little graph here. Guys, think of a good way to do this. Beautiful. Let's go to quadrant 1 and place in an angle. I will not place the entire unit circle. we're just placing an angle that terminates in quadrant 1. And I'm going to name that angle, not with a number, let's call it theta. Now what I'd like to do now is take a look at another angle, same size, but it's down in quadrant 4. It's down here. And I'll get out of your way here in a second. And I'll call this, since I rotate clockwise, negative theta. Same size angles, maybe both of them are 30, 30, 45, 45, 60, 60. One's in quadrant 1, the other one's down in quadrant 4. That's why I placed that prefix of a negative sign to make it rotate clockwise. Suppose I ask you to find sine of a negative theta. Express sine of a negative theta. Guys, if I do, me out here, and I want you to compare it to sine of the red one, theta. Let's think about what it looks like here. One's in quadrant 1. What is sine if you're in quadrant 1? The y coordinate. Everything's positive in quadrant 1. What is sine, the y coordinate, if you're down in quadrant 4?
Negative.
Negative. Does that sort of show me that this is equal to the negative of this? Since one's in quadrant 1, one's in quadrant 4, sine is positive in quadrant 1, sine is negative in quadrant 4. Does that now make sense why this statement is written like this? And that's where it came from. So I'll accept this as an odd function. Jacob, did I also do cosine?
Yes, you said cosine of negative theta
Okay.
equals cosine of theta.
Okay, something's a little different here. You gotta be very careful with this, guys. This one, just based on what I gave you on the handout right here, does it look more like this definition?
Yes.
Therefore, I would assume this is gonna be an even function. Say, Professor, why? Without a proof. Just a visual here. Guys, we do it right above here where I got a little room. And place my two angles, as I did before. Let's place that red one in quadrant 1 again. Just to make a comparison here. And we have it here in quadrant 1. Let's label this as theta. Let's go down to quadrant 4. The blue one, labeled as I did before. Same size angle. Let's call this negative theta. And you're asked now to look at the cosine of those angles. Nathan, if I do the cosine of the red one in quadrant 1, I know the answer's got to be positive.
Yeah, and so is the blue one.
See? Are they the same? And that's exactly what this even function tells me. So if I do a cosine, they have the same value. So it goes positive in this case. With me, guys? Making sense? Did I do tangent?
Yes, you did.
Okay, letter C. And Jacob, the way that handout gave that was more than likely tan of what? Negative theta?
Yes, equals negative tan of theta.
Beautiful. And without going through another sketch here, guys, this is what's going to be an odd function.
Yes.
Is that true, guys? Now, I could draw another sketch, but I could use one of the sketches I have already. I know and you know. If I'm in quadrant 1, tan is y over x. You're going to get a positive. If I'm down in quadrant 4, well, they said negative theta. If I'm down here and place y over x, what would I end up with down here? A negative. So that fits exactly what this right here tells me. This definition for an odd function. So this is an odd function for tangent. I don't think, when I created this worksheet for you guys, I don't think I mentioned secant, cosecant, and cotangent.
You did.
Oh, I did.
You said cosecant and cotangent are odd functions.
Beautiful.
And secant isn't even.
There you go. Okay. So now we know all 6. The way I remember these, Nathan, cosine and secant are the two even. the other four are odd. So if you have a cosine or a secant involved somewhere in your work, you recognize that maybe those are even functions, might help you, and the other four are odd. Jacob?
Couldn't you just simplify it to, if you just have any cosine involved, because secant's just the reciprocal.
Right.
So any cosine.
Exactly, if cosine has been identified as even, and then all of a sudden secant, which is its reciprocal, you would think, well, my goodness, it's also even. Because they're related, cosine and secant, and the other four are odd, okay? Now he said, Professor, is this gonna help me on the quiz Wednesday? I think it's gonna help you. Why would I do it? I think it's gonna help you. Now, part 3. Jacob, did I jump down to now a sketch maybe?
Yes, you said section 5.4 and 5.5.
Okay.
Graph of trigonometric functions.
Did I have a sketch down there somewhere?
No, you told us to sketch
Okay, and what was the sketch? What was the first one there?
It says f of x equals negative 3 cosine of theta over 3 minus 2x.
Pi over
Or,
3.
pi over 3, minus 2x.
Beautiful. I think, if I'm not mistaken, we looked at this right before the exam, maybe, last Wednesday. I think, or maybe the Monday last week. I think we've done this one before. But I need to do something a little different with it, which I think is gonna make it a little easier. Now, am I going to use transformations on Wednesday's quiz, because we see one like this? It's up to you. If you're going to go through transformations, I think many students by now will say, wait, Professor, if you're going to do transformations, I wish to turn this argument around. And what else might be suggested in that argument?
Take out the negative.
They got -2. Be careful, x subtract, what is that, 5 or 6? So guys, could I rewrite the original like this? Yes or no? Now, you guys would like transformations on Wednesday's quiz? Go for it. If you do, you've got to reflect through the x-axis. That's one graph, besides the parent graph. What, vertical stretch by a factor of 3. There's another one. All of a sudden, this. Negative inside there would be what? Reflection through the y-axis. The 2, what's the 2 do in terms of transformation?
It would make the period.
Yeah, it's gonna multiply all the x's by what, 1/2? So it could be what, maybe a stretch?
Yeah.
And then, or shrink, and then x subtract 5 or 6, you're not quite finished. What transformation would that be? A horizontal shift to the right, 5 or 6. Is that true? That would take you a good half hour to show me all those transformations along with the parent graph. Let me count again. The number of transformations would be 1 here, that's 1, 2, 3, 4, 5, along with the parent graph. Have fun. Can it be done? It can be done. So you guys who are good at transformations, you can do this, but you gotta show me 5 transformations along with the parent graph. I would prefer just to go to the final graph and not do all those transformations. Now guys, I don't know how many students remember what I did back last week to do like somewhat of a shortcut to get right to the final graph. First though, the reason I brought this back in, I think I did last week. Guys, is there a negative sign inside here? And it's a cosine. The function is cosine. Where is cosine? Oh. If there's a negative sign caught inside, that should be a reflection through the what, y-axis? Since this is a cosine, what can I do?
You can simplify
I
it.
can actually drop that negative sign. That's what this definition says. As you go from one side of that definition to the other side, is the negative sign dropped? So that would be 1, if you want to do transformation, that would be 1 that you are allowed to drop right here. It's gone from that definition. So now I'm looking at, if this would help you, let's call it y. Y is equal to -3 cosine, and Nathan, I'm left with inside here, if there's no mistake, this like this. You guys understand why I was allowed to drop that negative sign? Because cosine has been identified as even. I may do a sign here shortly. If this had been sine, not cosine, say same thing. I have that negative sign again here inside, but the function was sine. Look at the definition for sine being an odd function. Where does the negative sign now go?
In front of.
In front. This negative sign right here, inside here, we now travel out front, and I had a negative sign there to begin with. So when I take a negative out front with that negative, turns into a what?
Positive.
Positive. Now there would be a positive 3 to work with, if that had been a sign, and then I could graph it. Check it before I jump in and graph this one. Did I have, what was example number 2 for a graph? Was it a tan, cosine, secant?
G of x equals tangent of 1/4
Ooh,
x
I jumped into a tan.
minus 1.
Okay, and the last one has what function?
2 cosecant.
Oh, cosecant.
Pi over 4 minus x plus 4.
Okay, let's get this one out of the way, guys. Guys, the way I'm gonna approach it, I'm going to take it as this. Now, Nathan may say, Professor, no, I just want to leave it in the raw form up there, and I'm gonna do all those transformations. That's fine. If you can do all the transformations correctly, you'll end up with the graph I'm after. I'm just after the final graph. Now, I will do what we did last week. Did we do a somewhat of a bounding?
Yeah, we found it.
Now, be careful on the bounds. If you look back at the parent cosine graph, we should all know what that graph looks like by now. Can anyone recall what the parent cosine graph was bounded by, from what to what?
0 to 2 pi.
I want this one, the same thing, this 2 parenthesis x subtract 5 or 6. Bounded, but in a different color, between the same. Yes?
When you bound, can you use the original equation or do you use the one that you used the final one?
I think last week when I did this one, I used with that negative sign inside there. I think that's the one I did last week. You see this negative sign that we got rid of today because it's an even function? I think I used that negative sign and our inequality symbols reversed on us.
Yeah.
If you look back from the other problem we did. Laura, I would suggest you use the even odd property simplified as much as possible, and then use this form. Okay, guys, to solve this, divide through by 2, no problem. Add 5 or 6, no problem. I think it's 7, 5 or 6, watch my arithmetic here. And see if you guys agree. Are those the bounds? On the final graph. So it's going to start at 5 or 6, and it's going to end at 7, 5 or 6. Now, how many intervening points are there in between? Who recalls?
There has to be
3. Why? Because on the parent graph we had 0, pi over 2, pi, 3 pi over 2, and 2 pi. So I had 5 altogether. So guys, let's do this. Let's go to the grid. Try to make this work out for us. And let's place the 5 or 6 on the x-axis. Please leave enough space. I'm supposed to end at 7 pi over 6. Now, who recalls how does one determine the missing points in between? Who recalls? See, that's the sad thing. I don't see you guys enough.
The final
Yeah.
one.
Isn't it you add or subtract?
I'm looking for a key word first. What's that key vocabulary word I'm looking for right now that would help me to get a start?
Would it be,
Now see, Thursday, I didn't see you. Friday, I didn't see you. Saturday, I didn't see you.
Space bar?
Can you look at this one?
Yeah, what was that called? let's find the period of the graph. So on the side here, P for period, and that's merely, I heard Sophia say distance. Let's find that distance. Take 7 pi over 6, the ending, subtract the beginning. And guys, I think you end up with pi. Is that true?
Yeah.
That's the period. And then do what with it to have to find those 3 intervening points? Divide by 4. Why 4?
So you have 4 sections.
Okay, we have 4 quadrants we need to worry about, or 4 sections. Since there's 4 quadrants, so guys, let's take that period and divide by 4, merely that, and we'll call this my spacing. Susan, she sent out her beautiful notes that she always does, and I know she had this on the notes she sent out. I think it's the same problem. Okay, guys, there's some spacing. My goodness, let's see. Yeah, I see a 4 here and I see a 6 here. Let's come up with a common denominator to make it much easier. Let's change this spacing number to what? 3 pi over 12.
Yeah.
Easier for us. And then go to, is that going to be easier for us, guys? And change these to 12s also? So let's change this to what, 2 pi over 12? Just make it easier. And this one into what? 14 pi, I think it was, over 12. Yes or no? Now everything's in terms of 12. That means I'm with space by 12, so if I go at 2 pi over 12 in the beginning, add 3 pi, I'm at 5 pi over 12. 3 more, 8 pi over 12. 3 more, 11 pi over 12. And of course, 14 pi over 12. So we now have all 5 points we need. And by the way, keep in mind, this corresponds with 0 in the parent graph, pi over 2, pi, 3 pi over 2, and 2 pi. Now I'm ready to graph this. Now what's left here? Well, nothing here. You don't have to worry about this any longer. So if you want to just cover this up for a while, you need not to look at this anymore. What you need to focus on is this. What effect will this have? And I'm doing a cosine graph, so you gotta keep in mind what the parent cosine graph looked like to begin with. Now guys, on the side here, since I have not seen you for a while, Nathan, since you're close by, let's remind the class what the parent graph for cosine looks like. Jacob, can you recall where it started?
Yes,
For-
I
Start
can.
at 1,
Starts up at 1 at 0, right there. Then,
it goes down.
down to the axis.
And
Then,
then dips to -1.
thank you,
And then there, and then
back up. That's what it looks like this. That's the parent graph. Now what am I supposed to do with that in my mind? Flip it over, reflect it through the x-axis, it's gonna be upside down. As I make it upside down, they'll all also stretch it vertically by a factor of what? 3. Now, let's see if I can do it. Matthew, help me out. At the beginning, he tells me the parent was up at 1.
So it'd be a -1.
So will mine be at what?
It'd be a -3.
-3.
Yeah.
So we upside down and also stretch by 3. So mine's gonna be down here at -3 at the beginning. Let's put it right here. Matthew, tell me what's gonna happen at 5 pi over 12.
We would increase.
Okay, Tim, where's it located? Is it on the axis?
Yes.
Okay, how about the next point, 8 pi over 12, if you compare it to the parent graph flipped over?
We add +3.
Okay, it's gonna be up at +3, absolutely. Guys, it's gonna be up here, then back down to the axis, and finally back down to here. You guys agree? And now, if I connect, I don't have a mistake here, this is one cycle of the graph that we were looking for. It might look something like this. you're done. You're finished. If everything's good. Now, by the way, could I draw more cycles if I wish? Well, of course, there's an infinite number of cycles. You could draw more cycles to the left of this red graph, to the right of this red graph, and goes on forever. You guys agree? Now, if they ask you for the domain of the function, they want the entire function, not just this cycle. So since it does go forever, this is my domain. The range on the entire function, the up and down, see if you guys agree. -3 up to what? 3. Period, we found earlier, was pi. Is that true? Amplitude? Who recalls what amplitude should be here?
3.
Thank you. It is 3. And I think that looks good. I think that looks really good. Now, on Wednesday, if you're one of those students leaving a little late after the quiz, or after you have the quiz finished, I understand. You may be one of those students who say, no, Professor, I don't want to go to the final answer. I don't want to do this right now. I want to do all this business. Along with the paragraph, which will eventually take you here. I don't think, even though you can do it, I don't think many students will do it that way. I think most students will just go directly to the graph. Now, my MATH2 colleagues, and when I teach the calculus, you don't have the time to go through all those transformations. They're going to ask you, please go to the graph of this quickly, because I want you to do a calc technique on this. They're going to ask you to start drawing some tangent lines on this curve. Okay? Guys, any concerns here? Laura, did you sort of have that in mind?
Yeah, but when it comes to sign.
We're going to do a sign. Okay. Okay, guys? Now, let me do this for you. I may not graph it completely. Let me change it right here. This one's done. I finished up, guys. On the side here, she says, Professor, suppose it had been this, and the trig function was sine, not cosine, like you had. And it looked like this. And you do the same thing as we did. Turn this around. Take out a common factor of what? -2, I guess? Same as we did. Now watch carefully. That's what I did on the other. Now though, Laura and class, if you see a sine Wednesday, not a cosine function, sine has been identified as, where is it? Odd. This negative sign does not disappear. Where's it go? It moves out front. I love cosine because cosine just drops out. That's why I love the cosine graph, the even. No, here, since it's odd, you take this negative sign, can't drop it, out front, like it was here. And therefore you can rename this as y is equal to, by the way, since I had a negative sign there to begin with, we'll end up with +3 sine, and you're left with this. Close it up. Laura, then you'd go through the bounding, so forth and so on this. Almost like I did here, but similar to what I did. Okay?
So this one wouldn't be reflected, right?
Ah, beautiful, beautiful. This one has no reflection. This is the way we have it, it's going to be what? Vertically stretched by a factor of 3. And of course, this business, you take care of this with the bounding. And you used to have, like Ignacio told me, there's only one thing you need to worry about, stretch it by 3. There is no negative sign out front like I had in mind wherever it was, right here. I didn't have that here. Okay, I think that's good. Is that pretty good, guys?
Yep.
But you have to know what the even odd do for you to help you out here. Jacob, tell me the next one there that I have on the handout.
Tangent of 1/4 x
Hang on.
minus 1.
Put it on right here on the side, so you guys already have it on the handout. Part B, tangent of 1/4 x.
Minus one.
Oh, something else there. Subtract 1?
Yeah.
Let's go y. Okay, guys. Now, if you want to do it through transformations, a quick glance, I see only 2 transformations. That 1/4 is doing something for me, and that subtract 1 on the end is doing something for me. So this one would not be even too bad with transformations. If I do it through bounding, we'll see. Does anyone recall? Be very, very careful. Well, we bounded one of those, I think I had 3 cycles, and we're going to just need one. Give me one of those cycles and how we bounded it for the parent tan graph. Jacob?
I believe that we found it between negative pi over 2 and positive pi over 2.
Love it. Therefore, that 1/4 x, I'm bounding this based on last week between those 2 bounds. Guys, those bounds will change on you. If I did a cosine, my bounds were 0 and 2 pi. Now it says tangent, professor, we used in class between a negative pi over 2 and a positive pi over 2. You've got to know your bounds on these. Is that true, guys? Now let's solve this thing for x. Oh my goodness, multiply through by what, 4?
Yeah.
And I think, if I make no mistake here, you may end up with this for your bounds. Yes or no? Now this is gonna be fairly easy. That means now if I go to the grid, say, professor, I want to see what that one cycle looks like for this graph, tan 1/4 x, here goes. You guys, it says please start at negative 2 pi, I will, put it down here. And end at positive 2 pi, put it here. Now, someone in class tell me, we did the parent tan graph last week. How many points are missing in between? On the cosine graph, there were 3 points missing. How many points are missing compared to the parent graph on this one? Only 1.
And we know where it is.
Only 1. This is much easier. You just have to find 1 point that you say, professor, I think I see that what that 1 point is you need for tangent that falls in between negative 2 pi and positive 2 pi. Guys, it almost has to be what?
0.
0. That's all you need. I love tan. Very short, just 3 points. Cosine, a little heavier, 5 points. Sine, 5 points. Tan, 3. Now, does anyone recall what should be happening on the ends? Thank you. Vertical asymptotes, undefined. We have an asymptote here. And here. Oh my goodness, someone's going to help me out. We got the bounds done, we have everything done, this is done here, guys. All I need to worry about is this. What effect does the subtract 1 on the end indicate I should do?
Move it down 1 unit.
Vertically move it down, what, 1?
Yeah.
Down here, 1. I think it would be wise to draw the axis now down here at negative 1. You've shifted down 1. Here. Get this. Stay there for me. Now vertically shifted down 1. Now can someone tell me now, what does the graph look like? It's gotta look like its parent. What on earth does it might look like? And Jacob, I saw your hand going up, describe to the class, and I'll use your description to graph it.
On the left side, x is going towards negative infinity.
Like this?
Yeah, and then on the right side.
Wait, hold on now.
Yeah.
Get this graph in blue. Are you telling me based on the parent, it does something like this? There. Is that, and on the other side, I think you're telling me
It's above the axis and it
above,
goes
okay,
towards
and it's
infinity.
going over here,
Yep.
like this. Guys, yes or no?
Yes.
You think that's what the graph looks like? And that's one cycle.
No, we don't.
Now, before I start identifying the period, domain, range, and all that business, Levy, you got a question?
On this sheet, it says there's a left and right, but that's cycle.
Yeah, yeah. And this was tan 1/4 X, wasn't it? On the handout? Yeah, that's it. Guys, oh, by the way, does that somewhat look like the parent graph? Okay. The period on this one cycle, well, it's not the period. Period is the ending subtract the beginning. 2 pi subtract negative 2 pi, ending subtract the beginning, period of 4 pi. Some of my students emailed me and said, Professor, I found a shortcut to find the period. It's like a little formula in the textbook. In fact, I think on one of the handouts, I gave you a little formula you could use to find it. Ending, subtract the beginning. Amplitude, I must answer here, none. Amplitude is the highest point from the axis. This thing goes on forever. Period, amplitude, I need the domain. Now this is where it gets tricky. X cannot be where those asymptotes are located. Jacob, hang on just 1 second. I've got an asymptote here and an asymptote here.
Any multiple of 2 pi.
Can someone give me a good description when they ask for the domain, they want the entire function, not just that one cycle. So can anyone tell me what the domain might be for the entire function, all the cycles, where all we know at this point is I cannot use negative 2 pi and I cannot use positive 2 pi. Any multiple of pi or any even multiple of pi? Which one is it?
Any even multiple of pi.
I see even numbers, 2 and a negative 2.
It can be 0, which is technically.
0?
Isn't that a multiple?
0, no, wait, hold on now, 0 is even.
0 is even.
Yeah, 0 is an even number.
Then-
Do we have a graph correct?
Then it would be any multiple of 2 pi.
So now, okay, hang on. Now, if I do this, Sophia, that's why I slowed down here. You're saying, Professor, it's any multiple, make sure I spell that word correctly here, of pi.
No, it has to be 2 pi.
Okay, any multiple of 2 pi. With that, now tell me, if it's any multiple of 2 pi, where might, after I leave 2 pi here, that one cycle, where might the next asymptote show up? You think it's 4 pi?
No, it would be any multiple of 2 pi would
Okay,
be
help me out.
plus.
2 pi plus
Any multiple of 4 pi, but it is plus.
I need a good description.
X
And after you
plus
tell me what you think it is, I'll use it and see if sure enough, after 2 pi, there is an asymptote at that spot there. What-
absolute value.
Oh, no, we're not gonna do absolute value.
It could be 2
Ooh, let's
pi
not go there.
plus or minus any multiple of 4 pi,
Okay, a multiple of 4 pi, well, this one's not a multiple of 4 pi.
but 2 pi plus or minus.
Oh, 2 pi plus or minus.
Yeah,
2 pi plus or minus what?
any multiple of 4 pi.
Oh, you're gonna write that out, words for me also, gee.
Is it 6 pi?
Can anyone come up with a little formula?
2 pi plus 4 pi n.
Hold on, x cannot be, so tell me again, 2 pi
Plus 4 pi n.
plus 4, let's use, or a K, I'm gonna use K. Pi, something like that? I think your textbook uses it.
Oh, no, yeah.
That true? I'm gonna let K be any integer. Now I'm gonna check and see if he's got it here. So K is an element of the integers. I know Z represents the integers. So guys, he's telling me to replace K by any integer, professor. You know what integers are, no fractions. A negative or a positive though. And you'll end up with an asymptote. If I replace K by 0, I get 2 pi. If I replace K by -1, hold on, Lisa. How am I gonna get, okay. -1 would be what, -2 pi? And that's what we said here. Now, if I accept this formula, I replace K by 0, it looks like my graph shows it's correct. I replace K by 1, let's replace K by 2. If I replace K by 2, this is what, 8 pi plus 2 pi is what? 10 pi. So you're telling me the next asymptote's not gonna show up until you reach 10 pi out here. Oh, I knew tonight was gonna be it. If you guys, do you guys accept the graph?
Mhm.
Do we accept the graph?
Yeah.
Okay. And I'm trying to come up with a formula. Sophia's trying to come up with some words about multiples of something, which also would work if we can get it stated just correctly and pick up all those asymptotes. Lisa, I thought maybe you had it here then.
Well, actually, with.
Right, so it would be 6, hang on, if I replace K by 0, you get 2 pi.
Uh-huh.
That checks. I just throw numbers in there. If I replace K by -1, I end up with -2 pi.
Right.
If I replace K by 1,
Then you get
6 pi.
Yeah.
So are you telling me the next one will be 6 pi?
Yeah.
Yes.
If I replace K by 2, I think I did that earlier. And also, would you pick up an asymptote at, I think it was 10 pi?
Yes.
Okay, so you're telling me after 2 pi should be now 6 pi,
Yes.
then 10 pi, then probably 14 pi, yes or no?
Yeah.
18 pi, and I could do the same thing on the other side. So with what he gave me, would that pick up all of them? Just by that one simple formula. Sophia, did you come up with any words maybe, besides a formula that he gave me?
I just said the, like, 2 pi plus or minus any multiple of 4 pi.
Oh, 2 pi, plus or minus, you picked it plus and minus, any multiple of 4 pi.
Yes.
That's exactly what he's telling me. That's exactly what he's telling me, except he's telling me in a formula. And I'm sure there's different ways to express this. By the way, Issa, before I do this, we just said, if I replace K by 1, you get 6 pi. So if I go out to 6 pi, there should be something here that says, no, Ramsey, you can't use it. Let's see, 1/4 of 6 pi is 6 pi over 4. Reduce that down by 2. 3 pi over 2, unit circle says the order of pair is like that. And I'm doing a tangent. Tangent is y over x, -1 over 0, undefined. So that just sort of confirms there is an asymptote there, it's undefined. Okay, thank you so much. Nice little formula. Yeah.
Wouldn't you have to specify that K has to be an integer though?
Well, that's what this right here says. Z.
Oh, okay, sorry,
Don't scare me.
I didn't understand.
Yeah,
that
K
part.
is an
Thank-
element of, it's strange looking, E, element
Sorry,
of,
Thank you.
a set of integers. And I think I used a Z back in class for the set of
That's what I
integers.
was wondering.
So replace any integer here. Nathan, before I leave it, I know it looks strange. If I replace K by, for goodness sakes, 50, that becomes what, 200? Plus 2, that's what, 202? So if I was patient, by the time I got up to 202 pi, that should be an asymptote. So this just tells you all the locations of the asymptotes. That's all we're doing. Yes?
Could you please explain why is 2 pi plus, like, I don't get why is 2 pi plus 4 key. Like,
We're looking first at these on my graph.
yeah,
I'm trying to come up with is there a pattern there? Because you see there as a student thing, is there a pattern there? can I come up with somebody to express and find the next one? Now, I think the next one out here was 6 pi. You gotta come up on your own formula. Or write out in words like Sophia did. And then I could easily test it on a quiz or whatever and just replace k by a number at random, an integer, and if there's an asymptote there, you have a formula. It's gonna take a little business there, work with there. It's gonna take a little time to get used to this. Guys, just get the range out of the way. Thank goodness the range is easier. What's the range here?
Infinity, negative.
Absolutely.
You said there's no amplitude.
Amplitude is a number. Like this one had a number 3.
So even if we put a 7 in front of the.
No, hang on. Where am I? Back over here, you're saying to do something with this. Back here?
Yeah, if we put
No,
7.
you can read the graph.
Okay.
And you go look at the graph, and this graph goes forever. There is no set high number. You may say, oh, Professor, the amplitude is infinity. Infinity is not a number. So I cannot use infinity. That one's finished, thank goodness.
So if
Woo.
you had like 7 tan 1/4 x, you just.
Oh, no, I got you. If there was, out here.
Yeah.
Jacob, were you talking about maybe,
Yeah.
a coefficient out here? Then definitely you can, whoa, not on tangent.
So you'll never have one.
Nope,
That's what I was asking.
never.
Yeah, tangents always.
Always negative infinity through positive infinity. That's what you guys are thinking. You place a 7 out there and that could have an effect. It's not gonna have an effect on the range. Okay, guys, what's the last one, Jacob?
The last one is.
I gotta check my time here.
Cosecant.
2 cosecant of pi over 4 minus x plus 4.
Oh my goodness, what a nice quiz problem. Okay, here goes. Now I think that is, we'll finish this up here. Okay, Jacob, guy again. Y is equal to, what was it again?
2 cosecant
2 cosecant.
pi over 4 minus x plus 4.
Like this.
Mhm.
Now, if you, as a student, at this point in your math, if you could sit there on your own and get the graph of that mess, I applaud you. I applaud you. Now, keep in mind, this one looks much easier, but we got into some detail here with that domain on this thing here, that tan 1/4 x. Look at this mess. First, guys, I am going to do this. I'm going to rewrite the inside, rearrange it with the x coming first. What would you guys suggest next? Do.
The negative.
Take out the negative, like a factor, change this into this,
Move it all the way.
that's 4. Now, my lesson tonight. Cosecant on that handout, Jacob, I think we identified as an odd function. If it's odd, I don't get to drop the negative sign. I love dropping that, but I can't do it here. If it's odd, you are allowed to move it out front. Therefore, you can now rewrite this as y is equal to -2 cosecant, and guys left in there is this, plus 4. If we get through this one, we're gonna need a break. I'm gonna need a break. This thing is busy. Okay, here we go. I'm not gonna grab the parent graph. Oh, maybe I should. Some of my students may not have been with me last week. Oh my goodness. Let's put it on the side here. A little reminder. I'm about to finish this up anyway. Here goes, guys. Someone's gonna have to help me out here. I need a little reminder what the parent cosecant graph that we're accepting in this class, what it looks like. Does anyone recall where it started?
I over 2.
Yeah,
Pi over 2?
Yeah.
And it went out to what?
Then it goes up, it's kind of up to pi, but not reaching it.
Something else. I thought I graphed that right before you guys
It's,
took the exam. Your mind was probably on the exam.
What it is it's like parabola.
Somewhat.
So.
But I need to know, where did we start it?
You start at the peaks of
No, where do we start? Pi over 2, 0, 3 pi over 2, where did it start?
0 to 2 pi.
0 out to 2 pi, 0. Here we go. And I'm hearing, Professor, we went all the way out to 2 pi. This one, not like tan, this one has 3 intervening points. Guys, what do you think the intervening points here are for the parent graph? Pi over 2, pi, 3 pi over 2, of course 2 pi. Now I accept this as my parent. Does anyone recall what cosecant was doing on this parent graph at 0 at the beginning?
At 0 it was extending upward.
Is there an asymptote?
Yes.
Is there an asymptote at 0
Yes.
for cosecant? Because Professor, why? On the unit circle, I know on the unit circle at 0, the ordered pair is this. Is that true? If I can find cosecant at the beginning, 0, and its ordered pair is this, you're placing 1 over y for cosecant, 1 over sine. And we're placing what, 1 over 0? It's undefined. So you're going to start this graph out with an asymptote. You're saying, Professor, this class is going to get heavier, it's getting harder now. Of course it is. Then you're going to discover another asymptote at pi. We did this last week. And I think we stopped at 2 pi. I think Matthew was telling me something like this. Okay. I went through the unit circle. I tried to show you what the graph looks like. You guys are describing it something like little parabolas or something there. Did it go up to 1? I think. A -1? Yes or no?
It went up to 1, or it started at,
Was it 1 right here?
yeah, 1 there.
Okay.
And then both sides extended towards infinity.
Like this?
And then on the other side, it started at -1.
-1?
Both sides.
And something like this. Is that the way the graph sort of looked?
Yes.
Rough sketch. Oh my goodness, that was apparent. Now, you said, Professor, before the break comes up, we're graphing this mess. Good luck. Now, when I finish it up, it should resemble this. This is apparent. Does anyone have an idea, if I use bounding, what am I going to bound this by, based on what my bounds are on the parent?
2 pi.
0 out to 2 pi. Same thing here. 0 less than x subtract pi over 4. I know let me mess this up. Less than 2 pi. Nathan, sometimes I'll put less than or equal to. Why on the cosecant graph am I not going to use an equal to?
Because it has asymptotes.
As asymptotes. Now solve for x, easily done, just add pi over 4. And guys, looks like, help me out here, is that 9 pi over 4? I think. See if you guys agree. Now I know where my graph should start, where it should end, and then try to find the intervening points. And then all I need to worry about, Matthew, this business is done. I don't have to look at this anymore. I have to worry about though this and that. And we'll have the graph. Okay guys, let's finish this up, so I'm gonna take a break here. There's the parent. On the side here, guys, let's start at pi over 4. And go out to 9 pi over 4. And get this finished. Okay, pi over 4. 9 pi over 4, stretch it out. Let me find the period right quick, guys, of that one cycle. In fact, the period of the function. The ending, back to the beginning. I think it's 8 pi over 4. I think it's 2 pi, see if I'm correct. Is it 2 pi? Okay. Now, I need 3 intervening points like the parent had. Okay, let's divide by 4 on the spacing. Let's take that 2 pi period, divide by 4 to cover 4 sections, 4 intervals, 4 quadrants. I'm spacing by pi over 2. Is that true? What would you suggest, since I have a 4 here to work with and all of a sudden I have a 2 here? Let's leave this as 2 pi over 4. Let's leave the spacing as 2 pi over 4. So go to 2 pi over 4, add 2 pi over 4.
3 pi over 4.
3 pi over 4. Next would be what, 5 pi over 4? And finally,
7 pi over
7 pi over 4, I'm squeezing all this in. And it looks something like that. Nice. Now let me get ready for the conclusion. I do see eventually we need this. I think you guys would agree. And also I need to worry about that. Oh my goodness, someone's going to help me on this one. Does anyone have an idea of what might be happening? Hang on, guys. It's been what, vertically shifted up 4. It might be wise, since I've already shifted up there, to show the axis is now up here. We will not mess this up. Okay. And then from there, I'm supposed to stretch by 2, but it's upside down. Whoa. And I got asymptotes to worry about. Anyone tell me what do you think's happening at the very beginning of this graph?
Asymptotes.
Okay, let's put an asymptote in there. Right here, I think the same thing was happening at the beginning of the parent graph. Guys, let's put the asymptote in. I know it's beyond break time, hold on please. Then we're at, what, 5 pi over 4, might be the next one. And finally 9 pi over 4 out here, the next one. Okay. Those are my asymptotes. Now, can anyone venture out and tell me, as I do this in blue, no, let me do the graph in red. What's happening there?
We would be,
You gotta keep in mind,
It'll be negative.
negative, which means this, the little parabola you guys call it, on the parent graph, it was up here, I think. Where it might be on this one. Down here, and you gotta do what? Stretch what, 2 more. So I'm at 4. Where do you think this point will be when I do what I gotta do? Right here, 2? That true, guys?
yeah.
Okay, stretch by 2. And you guys are telling me, maybe, Professor, it's right in here somewhere? And is it gonna do this business, or is it gonna do this business?
Yeah, it's going down.
Okay, but like this. I'll put the arrows just to show you, it's forever. There's one branch. The other branch, I'm over here, I would assume, since I stretched down 2, I should stretch what? 2 here? That's going to take me up to 6 here. And should that one be opening up? I don't have this wrong to scale, guys. Yes or no? Woo! Jeez. Lord, I need to be paid more. Oh. You guys agree with the graph?
Yes.
Now, let's get this out of the way so we can take a break here. If we accept this, guys, domain. Let's get that one out of the way right now. X cannot be Sophia. Isa, help me out. I see there's an asymptote of pi over 4, 5 pi over 4, 9 pi over 4, I might expect the next one, if I should go out further, the next asymptote to show up at 13 pi over 4, 17 pi over 4, 21 pi over 4, and I can do the same thing on the other side. I need something, formula, multiples of something, to show how to find those asymptotes. Oh, let's try. Nathan, go for it.
Is it pi over 4, plus 2 over 4k?
Okay, 2 over 4 is 1/2.
Yeah, so 1/2 k.
No, just K.
Okay,
Okay, let me try. If I replace k by 0, these are integers. If I replace k by 0, you end up with pi over 4, and that agrees. If I replace k by 2, I'm gonna try 2, just random. Of course, I get a 1 there, so you end up pi over 4 plus 1. I don't see a pi over 4 plus 1. Did you mean to put a pi in this also?
yeah,
1/2 pi?
yeah.
Hang on. It doesn't work now. And you're saying now k, where k is an element of the integers. I'm gonna try now 2 here. If I try now 2 in your formula, 2 cancel. So it should be 1 at pi over 4 plus pi. That's what's pi over 4 plus pi gonna give me. 5 pi over 4. Whoa. Now let's test it at random. I tried 2, let's try 4. I put a 4 in it, let's try 3. I tried 3, we'll end up with what, 3 pi over 2. Here we go. Nathan, you may have something new. I'm adding pi over 4 to it. Common denominator of 4. Will give me pi plus, what is that, 6 pi, 7 pi? Over 4. Did I do that correctly? There's no asymptote there. Oh, I thought you had it. Guys, something else.
What if we just take out the 1/2?
Oh, just take out the 1/2. Just pi k?
Pi k.
Laura? I bet this is her concern. If I get any student just seeing this for the first time, it would be my concern. Okay, replace k by 0, trivial, it'll work. K by 1, if I replace k by 1, guys, you end up with pi over 4 plus pi. Common denominator of 4 gives me 5 pi over 4. Yes. Okay, let's try another one. Replace k by, that's k is equal to 1. Let's try k is equal to 2. Just testing. That would be pi over 4. Replacing k by 2 is 2 pi. Common denominator of 4, I think it's 9 pi over 4. See if I'm correct. Ah, there it is. Is that true? Is that giving me, with the help of the formula, where those asymptotes are located? Did anyone have maybe some words? Multiples, something like that you could use. Okay, we're about to close down. Okay, guys. Laura, class,
X.
this would drive me nuts as a student. You're saying, Professor, some of the other students in class are saying this so quickly and it's driving me nuts. You guys just trial and error, you gotta try something. And then try a few examples and see if it works. Can I give you a hint? I think I'll give you a hint.
Subtract.
Look at the difference between 2 of those asymptotes.
Yeah.
This one's at pi over 4, this one's at what, 5 pi over 4? The
Subtract.
difference is 5 pi subtract pi over 4. Is that 4 pi over 4, which is pi?
Yeah.
Is it consistent? 9 pi over 4 subtract 5 pi over 4, the other 2 asymptotes. What is that, 4 pi over 4? Pi. So you look at the locations of those asymptotes and end up with what you need there. You need pi, k, to work out. Nice. Range? Guys, I know we're way over time here. You're gonna get your 10 minutes here. Is that clock correct? Close to being correct?
It's pretty,
Is it 6:15?
Yeah.
yeah, pretty accurate.
Is it? Okay, so we're about 5 minutes over. Okay, here we go. Range, oh boy,
Negative infinity.
negative infinity, up to something though.
To two.
Up to
and
two.
six.
Two, including two,
Up, and then up to 6,
and 6
and then up to infinity.
to infinity. That's not too bad. Period, we got it out of the way, spacing, we got that out of the way, no amplitude on this. There's no highest point, this thing goes forever.
How would we write that as domain other than that, or is that the only way to write it?
This is it. Unless you come up with another version of this with a pi and a pi over 4 or something in there, could be another version. Some students like to use words. It's an odd multiple of this, or it's an even multiple of that. No. Most textbooks in calculus will ask you to do it like this. Got to come up with a formula. So you got to practice with that. Guys, do we have everything done here? Domain, range, no amplitude, period, get out of the way. I think that's it. Does it make sense? And that's just that one side of the handout. Okay. Now don't come back to me, you guys moving on to Math 7. Don't come crying to me. Don't knock on my office door. Nathan, I said, Professor, I need help, unless you got money. Big money. Yeah, Nathan, come on in, I'll help you. Let's try it with $300 for an hour. Yeah. No, guys, you need this though. You certainly need this. Those teachers are gonna be upset with you. And that's why some of the Math 7 instructors are upset with their students now. They didn't see this in detail when they had Math 2. They didn't see it in detail. They just saw the parent graphs and that was it. The instructor moved on to something else. Guys, any concerns here? I think we've done enough where I see some looks on faces like, oh no, I've got to really look at this. Okay, take your 10-minute break, my goodness.